Hello everyone, my name is Aditya Tiwari, Assistant Professor CS with you, Bhilai. In this tutorial, we cover the last operation of AVL 3. Already we covered the two operation, searching part and insertion part in the previous tutorial. Today we cover the deletion part or we can say the last operation of the AVL 3. So let's understand the concept of AVL tree. First, we have to understand the concept of binary search tree. That binary search tree we already covered in the tutorial in a binary tree tutorial also. Again, I repeat because the concept of binary search tree will be used in the for deletion of for the this topic, the AVL deletion tree. So deleting function is used to delete the specified node from a binary search tree. However, we must delete a node from a binary search tree in such a way that the property of binary search tree doesn't volatile. There are three situations of deleting a node from binary search tree. The node to be deleted is a leaf node. The first case is the leaf node we want to delete. Second case is it is the simplest. In the simple case, in this case, replace leaf node with the null and simple free the allocated space. In the following image, we are deleting the node 85 since the node is a leaf node. Therefore, the node will be replaced with null and allocated space will be freed. So, after removing the 85 node, which is a leaf node in a tree, the tree rest of the items, rest of the nodes are as it is as the same. Doesn't matter in the tree after deleting the 85 node. It means no any rotation will be operated, but might be possible after deleting the 85 tree will be a imbalanced tree. That is a property of AVL tree that we calculate by the balancing by the rotation operations. So we will see that thing in a future, but right now how we understand the concept of binary search tree. Here we deleting a 85 and 85 is a leaf node. So easily we remove that element from the tree, rest of the item are as it is the same. The node to be deleted, the second case, the node to be deleted has only one child. In this case, replace the node with the child and delete the child node, which now contain the value which is to be deleted. Simply replace it with the null and free the allocated space. In the following image, the node 12 is to be deleted. It has only one child. The node will be replaced with its child node and the replaced node 12 will simply be deleted. Here you can understand 12 is a grandchild of 50, it is a left successor of 25, as well as the 12 is a grand left successor of 50. It has only a single child in a form of 6 and 6 is a left successor of 12. 12 having only a single child in a form of 6. So, before deleting the 12, you have to replace the position of 12 from its child node, that is called as 6. So, after deleting a 12, 6 the child node will take the place take place of 12 and rest of the items are as it is. There is no any changes in the rest of the item. So, final tree is that one you are showing the figure. 6 will be take a place in a where the 12 is situated. So, this is a way to deleting a single children is available of any node and you easily replace that node from the tree. Now, difficulty when we facing a two children. Node to be deleted has two children. It is a bit complex case compares to other two cases. However, the node which is to be deleted is replaced with its in order successor or predecessor recursively until the node value to be deleted is placed on the leaf of the tree. After the procedure replace the node with null and free the allocated space. In the following image, the node 50 is to be deleted, which is the root node of the tree. Then we calculate the in order traversal. You know how we calculate the in order traversal. First we calculate in order traversal is the left, root, then right. So, we find out the sequence of this given tree, the in order traversal sequence. So, in a in order traversal sequence, first we find out the value of the leftmost item, then we go for the root, then we go for the right child of that tree. The final sequence of in order traversal is 6, 25, 30, 50, 52, 60, 70 and last one is 75. Now, I want to delete in this tree, in a given tree, we have to delete is a 50 item. Replace 50 with its in order successor, or we can also replace with the in order predecessor also. Here 50 having a successor item is 52 and the current predecessor item is 30. Both are the neighbor of 50. Either we replace by the successor value, either we replace by the predecessor value, but generally and most of the cases we can replace by the successor value. Now, 50 will be moved to the leaf of the tree, which will simply be deleted. So, as per the in order successor, so the neighbor of the 50 are 30 and 52. So, generally we can replace the value of 50, or we can say the root node by the in order successor. The in order successor neighbor is 52. So, 52 replace 50. So, the final tree is 52 become a root node of this tree. 25 as it is as a left successor of 52 and 75 as it is as a right successor of 52. Rest item all are the same, but removing on a single item, that is called the root node 50 and replaced by 52. So, this is a way how to we do to remove any item from a tree which having a 2 childs. But after deleting of either a 0 children, or we can say leaf node, or having a 1 children, or we having a 2 children in a tree, you always calculate the balancing factor of each and every node which is available in the tree, because when you calculate the balancing factor, then you find out the tree will be a balance, or we can say imbalance. Then we check the tree will be a balance or not. We will see in the AVL deletion operation. So, the deletion of AVL tree, deleting a node from an AVL tree is similar to that in a binary search tree. Deletion may disturb the balancing factor of AVL tree, and therefore, the tree needs to rebalance in order to maintain the AVL-ness. For this purpose, we need to perform rotations. The two types of rotations are L rotation, or we can say the left rotation, or another one is a right rotation. Here we will discuss R rotation, because you understand the concept of R rotation, you can easily, the L is a completely a mirror image of the right rotation. So, L rotation are the completely a mirror image. So, we want first to understand the only a single rotation, that is called a R rotation. If the node which is to be deleted is present in the left subtree of the critical node, then L rotation needs to be applied, else if the node which is to be deleted is present in the right subtree of the critical node, the right rotation will be applied. Let us consider that A is the critical node and B is the root node of its left subtree. If node X present in the right subtree of A is to be deleted, then there can be 3 different situations when we deleting a X element from the at the end of the right subtree. So, it will go for the 3 different type of situation. The first situation is the R0 rotation. 0, it means node B has balancing factor 0. If the node B has 0 balancing factor and the balance factor of node A disturb upon deleting the node x, then the tree will be rebalanced by rotating tree using R0 rotation. The critical node A is moved to its right and the node B becomes the root of the tree, and the T1 as its left subtree, the subtree T2 and T3 becomes the left and right subtree of the node A. The process involved in R0 rotation is shown in the following image. This is a tree where A is a root node, B is a current left successor of A, and B having a child in the form of T1 and T2 and both having a height is h. A also having a right child in the form of T3 where the height of T3 is a h. So, first we calculate the balancing factor. So, first we calculate the balancing factor of B. So, left is a height is h and the right of B has a height is h, again h minus h is 0. So, balancing factor of will be satisfied. Now, we calculate the balancing factor of A. So, in a way A at the left hand side we are having a generation 1 plus h, and the right hand side the balancing right subtree having only a single h. So, 1 plus at the left hand side we take the value 1 plus h, and at the right hand value is only h. So, 1 plus h minus h will be cancelled. The balancing factor of A is 1. Again the balancing factor of A is 1, it will satisfy the property of AVL tree because it comes under the range. Now, I want to delete an item from the right hand side right subtree of A, where the height of right subtree of T3 in the form of h. Now, delete an item, or we can say the generation height is the representing the generation. Now, we delete one generation from the at the subtree of right hand side of A. So, it will be at T3 having a height equal to h minus 1. After the deleting the x element from at the right hand side of A, so the height is h minus 1. So, again we calculate the balancing factor of each and every node. So, B is as it is. Now, we calculate the balancing factor of A. So, height left minus right, at the left hand side 1 plus h and at the right hand side h minus 1. So, h will be a cancel, but minus 1 will become a plus, that is why the balancing factor of A is 2. So, 2 is not satisfy the property of AVL tree because balancing range comes under the 0, 1 and minus 1, but here the balancing factor of A is 2, which is not satisfied. Now, in this case when tree or any node which is not satisfied, we go for the rotation operation. Now, how we identify which kind of rotation we can perform? So, you have to check the sign of the particular node where the balancing factor is not satisfied. Here we have only a single node which is not satisfied the balancing factor, that is called a root node, or that is a A. That the value is 2 and the sign is positive. So, at the positive sign we have to check the left hand side value, because we have to perform our rotation, or we can say the right rotation, because the positive sign always representing the weight at the left hand side is higher than as compared to the right hand side. So, we perform the right rotation. Now, which kind of right rotation? That is depend on the balancing factor of current left successor of root node. Here we having a left successor of root node A is a B, and the balancing factor of B is 0. That is why tree will be rotated at the right hand side with the rotation value is 0. So, in the R0 by the help of R0 rotation, or we can say the right 0 rotation, the tree will be formed in this way. A root node will be replaced by the B. So, B will become a root node. Now, B having a right child, B before rotation A is a root node that will be rotated. Now, A will become a right child of B, as well as B having a two childs T1 and T2. T1 is as a left child, T2 as a right child. T1 connected with the B as in the same form at the left successor of B, but the problem is that the right child T2 is a right successor of B, but we can't connect the at the right position because at the right successor already connected A. So, we can't connect it more than 2 children for any single node, which is not satisfy the property of binary search tree. So, we connected this T2 node at the left, at the position of left successor of A, and the T3 which is connected before the rotation connected at the as a right child of A, it is again he connected as it is at the form of as a right successor of A. So, only one changes, T2 will be disconnected from B as a right child and it should be connected as a left child of A. So, finally, tree after the rotation in this form. Now, again after performing the rotation, again we calculate the balancing factor. Now, the balancing factor of A is again 1 and the balancing factor of B is height of left is only h and height of right is 1 plus h. That is why h will be cancelled and the balancing factor is -1. So, the -1 it means comes under the range. So, we can say after the performing the R0 rotation, the tree will be a balanced tree. We take another example in how we calculate that one. Suppose we have this is a tree, we are having a 20 is a root node, 10 is as a left node, 30 as a right node of 20 and 5 and 15 both are the children of 10 left as right respectively. Now, here we want to delete an item 30 from the tree. So, before deleting an item 30, first we calculate the balancing factor of this tree. If each nodes are satisfied or not the property of AVL tree. So, first we calculate the balancing factor of leaf node 5, 15 and 30 all are 0. Then we calculate the internal node 10, again the balancing factor of is 0. Then we calculate the balancing factor of 20, that is a 1 plus 1, that is my 2 minus 1, it means a 1. The balancing factor of 20 is 1, again satisfy the property of AVL tree, where all the values, all the balancing factor comes under the range of the AVL tree, that will satisfy the property of AVL tree. Now, we have to delete an item 30 from this tree. In this case, the node B has balancing factor 0, therefore, the tree will be rotated by using a R0 rotation as shown in the following image. The node B10 becomes the root while the node A is moved to its right. The right child of node B will now becomes the left child of node A. So, after the performing the rotation, after deleting the 30, the tree will be imbalanced tree. So, we perform the R0 rotation. So, 10 will become a root node, then 20 as a right child, 5 as it is a left child and 15 will be disconnected from the as a right child of 10 and it will become a left child of a 20. So, the final tree is in this form, or again we find out the calculate the balancing factor of each and every node, which is satisfy the property of AVL tree, where the all the nodes having a either of balancing factor 0, 1 or -1. So, all are comes under the range of AVL tree. Now, we go for the second one operation, that is called a R1 rotation. Suppose node B has balancing factor 1. In the last one we done a operation by the where the balancing factor of B is 0. Right now, the balancing factor of B is 1. So, R1 rotation is to be performed if the balancing factor of node B is 1. In R1 rotation, the critical node A is moved to its right having subtree T2 and T3 as its left and right child respectively. T1 is to be placed as the left subtree of the node B. The processes involved in R1 rotation is shown in the following image. So, here we having a tree, there is A is a root node, B as a left successor of A and B having a 2 childs T1 and T2 and both having a height T1 height is h and T2 height is h minus 1, where the T3 also is as a right child of A and where the height of T3 is h. Again find when we calculate the balancing factor, which is comes under the range, so no issue. Now, deleting an item from at the right hand side of the T3. When we deleting an item, so is the height is h minus 1. So, again we calculate the balancing factor of after deleting an item x from the right hand side of A. So, the balancing factor of B is 1 and the balancing factor of A is 2, which is not satisfy the property of AVL tree. So, we go for the rotation operation to tree will be converted into a balanced tree. So, which kind of rotation we perform? By the sign operation, by the sign. So, here only A which is not comes under the range, A balancing factor is not come under the range. Here the value is 2 and the value is 2 is will be in the positive. So, we go for the right rotation. Now, which one rotation? In a 0, 1 or minus 1, then we check the current left successor. So, left successor having a value is 1, that is why we perform the R1 rotation. Then R1 rotation, just simply do it. B will become a root node, A will be shifted as a right child of B, T1 will be connected as it is in the form of left child of B as a left successor of B, T3 as it is a right successor of A, only one difference T2 which having a height is h minus 1, it will be disconnected from the B and it should be connected as a left child of A. This is a way how we connect a item T2 in a new tree. Again we calculate the balance after the rotation, again we calculate the balancing factor of this tree. So, the balancing factor of tree is B is 0 and again A is 0. It means all nodes are satisfying the property of AVL tree which has come under the range. So, we can say after the performing the R1 rotation, the tree will be a balanced tree. We can understand by this example. Suppose we having items like root node 50 and lot of the item is available 40, 60 like that. Now, first we calculate the balancing factor of this tree. So, if we calculate the balancing factor all the leaf node like 10, 30, 45, 55 all are 0, then we calculate the balancing factor of internal node 40 and 60 both are 1. Then we calculate the balancing factor of 50, that is also a 1. So, the trees have no issue. Now, when we deleted a new item that is called a 55, now we delete an item 55 from this tree, what will happen? So, simply remove 55 from this tree. So, 55 is a leaf node, there is no issue as the situation of binary search tree, because 55 can be easily remove that node from the tree, no any impact in the tree. But we have to cross check the balancing factor after deleting the 55. Deleting 55 from the AVL tree disturb the balancing factor of the node 50. It means node A which becomes the critical node. This is the condition of R1 rotation in which the node A will be moved to its right as shown in the image below. The right of B is now become the left of A, it means 45. The process involved in this solution is shown in this image. So, before deleting of 55, the tree will be a balance. After deleting of 55 from the as a 55 as a left successor of 60, after deleting of 55, the tree will be a unbalanced tree, or we can say imbalanced tree, because the root node does not satisfy the property of AVL tree. Here we having a value of the balancing factor value of 50 is 2, which is not satisfy the range of AVL tree. So, we go for the rotation operation. As per the sign, we can understand positive sign, so we go for the right rotation. But which kind of right rotation, 0, 1 or minus 1, that is we can then we see the balancing factor value of current left successor of root node. So, the current left successor of root node is 40 and the balancing factor value is 1. That is why we go for the R1 rotation. Then R1 rotation, 40 will become a root node, 50 will become as a right child of 40. The rest of the item, the 30 and 10 both are the left successor as it is connected to the 40. Only one difference is that 45 will be disconnected from 40 and should be connected as a left child of 50, and 60 as it is a right child of a 50. So, after performing the R1 rotation, tree will be formed in this way. Then after the performing the rotation, again we calculate the balancing factor of each and every node of this tree. So, all the leaf node having a balancing factor are 0. So, then we calculate the balancing factor of internal node. So, 30 balancing factor is 1 and the next one is the 50 is a 0, and we calculate the balancing factor of the root node 40, again is a 0, because height of left or height of right are both are same. So, h minus h is, it means 0. So, after performing the R1 rotation, the tree will become a balanced tree. Now, we go for the last operation, that is called a R minus 1 rotation. Here the node B has balancing factor is minus 1. R minus 1 rotation is to be performed if the node B has balance factor minus 1. This case is treated in the same way as LR rotation, left right rotation. In this case, the node C, which is the right child of node B, becomes the root node of the tree with B and A as its left and right children respectively. The subtrees T1 and T2 becomes the left and right subtree of B, whereas T3 and T4 becomes the left and right subtree of A. This process involved in R minus 1 rotation as shown in the following image. So, the tree we have A is a root node, B as a left successor of B, and all are the T1, T2, T3 and T4 are connected with this its nodes. So, then we calculate the balancing factor of this tree. Here we having a balancing factor of this tree, C is again 1, B is again 1, B is minus 1 and A is again 1 at the left hand side, 1, 2, 3, 3 minus 1, that is again a 1. So, the tree will be a balanced tree. Now, we calculate the, after deleting the x element from the right hand side of the right subtree of node A. So, here T4 having a height h, now after deleting a x element the height is h minus 1. Now, again we calculate the balancing factor, which is not satisfied because C having a 0, B having a minus 1, but A having a 2 balancing factor. So, 2 balancing factor which is not comes under the range of AVL tree. So, if we go for the rotation operation. So, by the sign we can understand which kind of rotation, that is a right rotation, where the balancing factor of A is 2, that is a positive sign. So, if we go for the right rotation. Now, how we calculate the which kind of rotation, 0, 1 or minus 1. So, we go for the, we can cross check the balancing factor of current left successor of A. So, we have here we having a B as a left successor and the value of the balancing factor of B is minus 1, that is why we go for the R minus 1 rotation. In R minus 1 rotation, or we can say the LR rotation, left right rotation. In this rotation, we replace a root node by the grandchild node. We can't replace by the either a left child or the right child. Here we go for the right rotation, that is why we take a grandchild of the grandchild of the left hand side. That is why here we having grandchild is a C, it is not a B. B is a current child, but C is a grandchild. So, A is replaced by the C. So, C will form a or become a root node of this tree. Rest of the item B are as it is as a left successor of a root node. Now, right now root node item will be changed. In the previous one is the A, and right now it is replaced by the C. A should be rotated at the right hand side and A will be connected as a right child of C. So, B as a left child of C and A is as a right child of C. Now, T1 and T2 both are the children. T1 is children is a T1 is as a left children or left successor of V, but here we check the T2 child before rotation, T2 as a left successor of C. Now, C will become a root node, C having no any edges to connect it, because already 2 edges are connected, 2 children are already connected in the form of B and A. So, we can't connect it T2 or T3 to directly with C. Now, T2 will connect it as the right child of B. So, T2 will be go at the as a form of right child of B. Now, T3 will be disconnected from C and should be connected as a left child of A. So, T2 go and connected with the as a right child of B and T3 is connected as a left child of A, and rest of the items like T4 as connected as it is as a right child of A. So, again we after the connecting all the children to his parents, now again we calculate the balancing factor of this tree. So, the balancing factor of B is again 0, A is 0 and the balancing factor of C is again 0, which comes under the range of balancing factor, or we can say they follow the property of AVL tree. That is why the tree is completely a balanced tree. So, this is a graph we can understand how we convert or how we rotate the rotation part, and we easily shift to a imbalanced tree to a balanced tree. We can understand by this example. Here we having elements like here we having a 50 as a root node, 40 and 60 as a left successor and right successor of 50, and 45 as a right successor of 40. Now, before anything we have to calculate the balancing factor of each and every node. So, the balancing factor of nodes are 45 is 0, 40 is -1, 60 is 0 and 50 having a balancing factor is 1, which comes under the range of balancing factor, or we can say that this tree is a AVL tree. Now, we have to delete an item 60 from this given tree. In this case, node B has balance factor -1. Deleting the node 60 disturb the balancing factor of the node 50 also. Therefore, it needs to be R -1 rotated. The node C, it means 45 becomes the root node of this tree with the node B 40 and A 50 and as its left and right child respectively. So, after deleting a 60, you again calculate the balancing factor of each and every node. You cross check, the balancing factor of 45 is 0, balancing factor of internal node 40 is -1 and the balancing factor of root node 50, that is a 2. So, again we cross check which kind of rotation we can perform. By this sign we can understand we go for the right rotation, and also we have to cross check which kind of number we have used 0, 1 or -1. We have to cross check the current left successor of root node, that is called a 50, and 50 having a balancing factor in the form of -1. It means we go for the rotation operation is R -1. So, as per the rules of AVL tree or the rotation part, where the balancing where we go for the rotation is R -1. So, 50 or root node where we having a problem in any node, it should be replaced by a grandchild node, not as a current child node, or we can say or a successor node. So, we have to find out the in-order traversal. By the in-order traversal, the item is 40, 45 and 50. Again as I told you, either you replace particular node by the in order predecessor, or we can say in order successor. Here we having only a single rotation, that is called right rotation. That is why we replace that particular item by the predecessor value, not by the successor value. But in a mirror image, suppose you are working on the left rotation, you can replace by the successor value, because at that time we do not have any predecessor value. But here we having only a successor value, that is why we having a predecessor value, that is in the form of 45. So, we replace that particular node which is not satisfy the property of AVL tree, that is a 50, that is a root node. It should be replaced by the grandchild node, that is a grandchild node, also a predecessor node, that is a 45. So, 45 will be take as a place in the form of 50. Now, 50 will be shifted as a right child and 40 will be as it is as a left child of 45. So, after the performing the rotation, the R -1 rotation, or we can say the left right rotation. So, again we calculate the balancing factor. So, the balancing factor of all the nodes are the 0. So, this way we can say the tree will be a balanced tree. So, we understand all the rotations part, R0 rotation, R1 rotation and R -1 rotation, and after all kind of rotation our tree will be a balanced tree. In a same mirror image, we have all other 3 operations like L0 rotation, L1 rotation, L -1 rotation. It means a left rotations. Here we check only one part, that is a right rotation, but 3 parts are also left, that is a left rotation, L0, L1 and L -1. That is a completely a mirror image of this rotation. And what we done in the last slides, why the rotation part R0, R1, Y1, same as it operation you can do as a left operation also. So by this rotation we can do that tree will be a balanced tree. Thank you.